Hey everyone, thank you for coming. So I just wanted to get a bit of a feel for who's in the room. So can I get a show of hands? How many people are administrators on Atlassian applications? All of you. Perfect. Okay, I think you're in the right spot. So how many of you have run out of memory in one of your applications and had to tune to fix it? Again, almost all of you. Cool. Did anyone manage to fix it easily? A couple. Okay, good for you guys. Did anyone end up with worse problems when you started to mess with it? Yeah, a couple. Yeah, so that's exactly what happened to us earlier this year. We started off with a small problem and we had a couple of outages, and over the next few months we tuned ourselves into a really big problem, and then we managed to tune our way out of it again slowly. So I want to talk to you a little bit about that. Then we're going to go through some of the basics of garbage collection, some troubleshooting tips, and some tuning best practices. So we are going to go through some pretty technical topics. Don't worry about writing it all down in notes. This will all be recorded, so you can revisit everything later. So the question that I've promised to answer today is how to reduce downtime by tuning garbage collection. The answer to that is almost always don't tune. So the defaults are saying if you can avoid it, don't mess with it. The defaults make the most sense for the most people, and on top of that, the JVM is built to react adaptively. So it's taking real-time data, and it's configuring itself in the best possible way on every single collection. So lastly, the knock-on effects can be pretty hard to predict. I kind of think of it a little bit like chaos theory, where if you have a butterfly flapping its wings in one part of the JVM, something really weird happens in another. And that's essentially what happened to us. So at the start of the year, I was tasked with looking after EAC, which is our internal intranet system at Atlassian. So it runs on Confluence data center. We've got 3 nodes. They're all on VMs, and they have about 5.5 gig of memory each. So a lot of you know what it's like to be sysadmins in big companies and big instances. We have a lot of people who are responsible for this system. So we have a team to bring it back up when it goes down. We have a team who manage the VMs, a team who do the administration work on it, and the Confluence engineering team, which I'm part of, who manage the upgrades and root cause analysis of outages. So there's another level of complexity here again, in that we're using these instances for dog fooding. So we update just about every single week. And sometimes it can be hard to tell if something's a bug or a tuning problem, because it's likely to be the first time it's ever been seen. So we have around 1,250 daily users in this system. It might not sound like a lot to some of you, probably have much bigger instances, but it's about 3/4 of Atlassian. And a lot of those people just live and breathe EAC. So in Atlassian, it doesn't happen unless it happened on EAC. It's our living record. It's where decisions get made, where wins are celebrated, and where the hard questions get asked and answered. So it's what allows a company with so many new employees to get people onboarded and ramped up quickly with context. So in my opinion, it's the sole largest contributor to our culture. So without it, we really wouldn't be the company that we are. So when this system goes down, a lot of people can't work, and there are a lot of eyes on you. So it can be pretty high pressure. So in fact, it's not even unusual to get a call from Mike or Scott when things go really wrong. So we had some outages, some reports of slowness, and we went looking in the logs, and what we found was that we had 8-second garbage collection pauses. So hands up, who thinks we should add more memory? Anyone? No? Okay. Well, that's actually what we did. We just assumed, garbage collection problem, more memory, problem solved. We didn't think about it too much. We just increased the memory up to 8 gig. So, we thought we'd fix the problem again. Well, we end up with 50-second garbage collection pauses, which is not great. And that was really our first mistake. So I mentioned before there's a lot of division of responsibility for this system. And the people who requested the increase weren't the people who made the change, and the people who made the change weren't the people who owned the VMs. So we increased the memory available to Confluence, but we didn't check how much memory was available to the VMs themselves. So if a VM doesn't have enough memory for a process, it takes space from the hard drive and it writes memory to that, which is a process called swapping. And so we'd given 8 gig to Confluence, but we actually only had 8 gig available to the VMs. So we were hitting that swap file pretty hard. And so every time we garbage collect, we're having to load memory from physical drives, which is a lot slower. So we figured that out. We bumped from 8 gig of memory to 10 gig of memory available to the VMs. So we have a 2 gig buffer in between what we've got allocated to Confluence and on the VMs. And we disabled swapping entirely, just in case. And we figured we'd solve the problem again. So what do you reckon? Hands up. Is the problem solved? No. Nope. True. We got back down to 45-second pauses. So we managed to claw back 5 seconds of pause time by getting rid of swapping. But at this point, we realize adding more memory really isn't going to help. And we need to understand the pauses. And to do that, we just need to understand garbage collection better. So this is a pretty complex topic. We can kind of go down the rabbit hole with talking about how garbage collection works. So I'm just going to keep to a high-level overview. So the Java heap is split into two main areas. You have young generation, which consists of Eden and survivor spaces, and that takes up about 40% of the heap. And you have old generation, or tenured, which takes up the other 60%. Now, when an object gets created, it gets created in Eden. And when Eden starts to fill up, you have a partial garbage collection, which operates just on the young generation, so Eden and survivor. And the first thing it does is it marks all objects that are still in use, and it will delete any that are no longer being referenced, and promote the objects that are still in use over into survivor. Now, when Eden fills up again, you have another partial garbage collection, and that will clean out the objects no longer being referenced in Eden, and any no longer being referenced in survivor, and anything that's still being referenced at that point will get moved over into tenured. So when tenured fills up, a full garbage collection operates on the entire heap, and that will leave any object that's still in use and delete anything from tenured that's now no longer being referenced. So the idea behind it is that objects are either very short-lived or very long-lived. So the objects that are likely to be long-lived, you want to move them into another part of the heap, so you don't spend time trying to clean them up on the most frequent collections, which are your partial collections, because they're likely to still be in use. So there are two main types of collectors that you can choose from, and the main difference between them is whether they stop the application running while they collect garbage. So serial and parallel are pretty similar, and they are both stop the world, which means that they will stop all of the application threads running, then they will perform the garbage collection, and then once it's finished, they start all the application threads running again, which means your application will pause for that entire time. Concurrent collectors, on the other hand, do a lot of their collection work while the application is running. And there are two types of concurrent collectors. You have concurrent mark sweep, or CMS, and G1GC, or garbage first. And now G1 replaced CMS, so it's pretty much what we refer to now when we talk about concurrent collectors. So serial and parallel are both stop the world, so they pause the application, collect garbage, and then start the application up again. The only real difference between them is multi-threading. So serial is single-threaded, and parallel is multi-threaded, and parallel is the default collector. So if you don't specify one, that's the one that you'll get. They generally work better for smaller heaps, because smaller heaps are faster to clean. So it's going to be much quicker to stop the application running while you clean 2 gig than trying to stop the application and clean out 10 gig. So with a smaller heap, those pauses are likely to be so short that your users won't notice them. So when is it better to use serial or parallel? Basically, if you have occasional spikes in workload. So things like a space export for Confluence, they use a lot of memory, but they're not run very often. So if your usage is otherwise pretty low, you can use a parallel collector. So you're throwing a lot of horsepower at those spikes and cleaning out those objects really quickly, but you'll be spending less effort doing garbage collection the rest of the time. So for G1GC, instead of doing stop the world full garbage collections, it cleans the tenure generation concurrently while the application is running. So there are still some pauses. Some phases of the collection just need to ensure consistency, but they're much shorter than a full GC with a parallel collector would be. So you need to have a larger heap for G1GC, and it's mainly because of the way that the heap is laid out. So if you're using a serial or parallel collector, the heap is split into large contiguous blocks of memory. So you have Eden, Survivor, and Tenured, and it's all contiguous. Whereas G1 will split the heap into 2,048 non-contiguous regions, and it will allocate each region to Eden, Survivor, or Tenured as it's required, and it will leave the rest unallocated. So it's called garbage first because it cleans out the tenured regions which have the most garbage in them first. So it doesn't clean every region on every collection. It just aims for the ones that will give it the most reclaimed space for the least amount of effort. So it needs a larger heap there because there's always going to be some dead objects in regions that have yet to be collected. So when is it better to use G1GC? Well, G1 can actually be a little bit slower during normal operation, especially in a smaller heap, but it will take away those huge pauses that you get on a large heap with a parallel collector. So G1 spends more effort doing garbage collection, so there's less of your resources available to run the application, which is why it's a little slower, but it takes away those huge bad pauses. So use G1GC if you need to have a larger heap and you can't afford to have long pauses. So there is a bit of a gotcha with G1GC, and that is that young generation collections are never concurrent. So They're parallel by default, and there's no way to make them concurrent no matter what collector you use. So if you have a really large heap and you're using G1GC, you might think you're not going to have any pauses, but young generation collections will always pause. And the larger the heap, the larger your young generation will be as a proportion of it, and the slower those collections will be. So young generation collections are the most frequent, and if they're taking some time to run, then your users might actually start to feel some slowness. So pause is inevitable no matter which collector you use. It simply can't be engineered out. But you can decide what types of pauses you have and whether you want longer pauses but less of them, or more frequent pauses but shorter in length. So let's have a look at some of the types of pauses that can occur. You have young generation pauses, which are common, but they're usually pretty quick, and they happen with all collectors. The most commonly problematic pause is your full garbage collection if you're using serial or parallel, and those are usually the really long ones that start to cause big problems. The pauses in the concurrent collectors are the mark and remark phases and in two-space allocation, so when it's trying to allocate regions. So when the collection starts, there's a pause for the initial marking of objects, and then the collection will happen concurrently while the application's running, and then it will pause again at the end, just small pauses for remarking and some cleanup. So for two-space allocation pauses, so grabbing those regions and allocating them to Eden, Survivor, or Tenured, they happen if an object needs to be promoted from Eden to Survivor or Survivor to Tenured, but there isn't any space in an already allocated region. So G1 will grab a new region and try and allocate that. But if it can't, it's on the verge of a pretty dramatic failure. So it will pause and clean and try and reclaim enough space to be able to allocate a region. So if that fails, then you have a failover full garbage collection, which will pause again. So in our case earlier in the year, that's the type of pause that we were hitting. Now there's currently a bug in Java that means this collection is really, really slow. It's fixed in Java 9, but obviously that's a while off for us all. So we really need to avoid this at all costs. So with G1GC, 10% of the regions are reserved by default, and they're never allocated until a two-space allocation failure happens. So if an object can't be promoted, the collector will grab a reserved region, allocate it to whatever is required, and continue. So we were seeing some short two-space allocation pauses where reserved regions were used, and then much longer ones where there was no free region to allocate, and the collector had to pause and try and clean enough to free a region up. So those were our 45-second pauses. So we increased that reserve percent to 20%. So out of our 8 gig heap now, we have 1.6 gig of that reserved at all times just for an allocation failure. But a few days after we increased it, we had another outage. So we tried to be good sysadmins, and we assumed that our change was not successful, so we reverted it. And as a lot of you probably know, troubleshooting data center outages can be pretty complex. It can take a little time to get to the root cause because there are so many moving parts. So it took us about a week or so to get to the root cause of that one, and it turned out to be database connections and nothing to do with garbage collection at all. But by that stage, we'd already reverted the change, and we assuming that it hadn't worked, and we kept on having outages. So that was really our second big mistake. We didn't measure the impact of the change that we made. We relied on outages as a measure of whether the change was successful. What we should have done is benchmarked, measured the number of pauses, the length of them, the time in between them, and used that to determine success or failure. But by this time, we'd forgotten about the reserve percent. We had a lot more outages, did some more diagnosis, tried a few other things which didn't help either. And after a month or so, we sort of ended up looking back at that reserve percent. So at that point, we started to crunch some numbers. And we found that even though it wasn't a very long time, when we had that reserve percent set to 20%, we saw some short two-space allocation pauses where reserved regions were being used, but no 45-second ones. So we bumped that up back to 20%, and we kept a close eye on the logs, and we ended up with under 1 second pauses. So the lessons that we took away from that experience was really that GC is really hard, although to be fair, I think we probably knew that already. But there are a lot of moving parts, and changes you make can affect a lot of different areas. Sometimes your fixes can make things worse, and on top of that, sometimes you can fix things and not even realize that you fixed things. So the biggest lesson we took away from all of this is really the need to benchmark. So you need to measure things, have a plan, and execute that plan, even in high-stress times like big system outages. So you need to know what success and failure looks like, and that needs to be more granular than just did the system go down again. So if we'd said the measure of success here was to run for 2 weeks without any two-space allocation pauses over 1 second, we would have been able to put this incident to bed a lot earlier, and we probably would have saved ourselves about 5 or 6 outages. So the moral of my story here really is that if you're going to tune your garbage collection, you really need to plan, benchmark, make small changes, measure the impact of those changes, and then repeat. So let's have a look at some tools that can help you do that. So here's what your average garbage collection log looks like. And this is a heap using G1GC. So at the top, you can see a bunch of information about the heap, including whether you're using the swap file. And here you can see partial GCs occurring on the young generation. This particular one took 0.08 seconds. And it cleaned out 525 meg from the young generation, taking it from 600 meg down to 75 meg. And you can also see the full size of the heap is 11 gig. So you can see here where the concurrent GC events are starting. And you get the pauses in the concurrent phase. As you can see, they're all really short. And here you get the end of the collection. So if you turn on more detailed GC logging, you'll get events that look like this. So this is a concurrent collection with G1GC again, just like the previous one. It's just a bit more detailed. So the first thing you'll get there is you see the reason that the garbage collection began. And in this case, it's because 12.5% of the old regions contain enough garbage to warrant a collection. And that can be really useful if you're having frequent collections kicking off and you're not sure why they're starting. So then you get a lot more detailed information about each phase of the collection, and that can help you troubleshoot specific pause problems or specific phase problems. And you can see the results of the collection at the bottom. In this case, Eden went from full at 584 meg to completely empty and resized down to 216 meg. Survivor went from 34 to 40 meg, so it's had 6 meg of objects promoted from Eden. And the overall heap went from 3.7 gig out of 5 gig down to 3.1 gig. And lastly, at the bottom, you see the full pause time for the collection, which is 0.03 seconds. So again, there is some pause, but it's quite short. So these are not particularly easy to read, and they are incredibly hard to see patterns in. But luckily, there are some tools that will help you visualize these logs, which can give you a much clearer picture of what's going on. So my favorite is GC Viewer. It's not very flashy. I think it's built in Swing, but it's free, and it has everything that you need. So firstly, the size of the heap is marked out on the left. You can see this one is a 1 gig heap. And you can see how much is allocated to each generation. So the young generation is marked out in yellow, and the tenured generation is the pink at the bottom. So along the top, you see the server time. So you can correspond those with reports of slowness or particular outages, and you can see visually what was happening in garbage collection at that time. Along the left, you have pause times in seconds. And down the bottom, you can see there's a bar for each garbage collection. So this is just basically like a bar graph that's been superimposed over the top of that timeline, and that corresponds with the pause times on the left. So you can see in this case, they are almost all under 0.1 seconds. So the blue line running through the middle, that tracks how much of the heap is being used. So you see it go up and down a lot with every collection. Now, this is a system starting up, so you can see there's a lot of activity at first, and then it really starts to settle down. Now, that sawtooth pattern you see starting around the middle is what normal young generation collections look like. So you can see in this instance, once that sawtooth pattern begins, heap's filling up to about 850 meg. And with each partial collection, it's dropping down to 600 meg. So the black lines you see here are full garbage collections. That's when you'll see the baseline of that blue sawtooth pattern drop quite dramatically because a lot of space is being cleaned out of the tenured generation. And this is another healthy garbage collection log. You can see that sawtooth pattern happening again. And you can also see that young generation is resizing itself quite dramatically, even during normal operation. So in this case, it's going from 500 meg to 4 gig in a matter of seconds and back again, and that's completely normal. But if you start setting the size of those generations explicitly, then you stop the JVM from being able to do this resizing when it needs to. So if you flip over to the Event Details tab in GC Viewer, you get a lot of collated information about the different pauses. So you see the types of pauses, the minimum and maximum, and a count of how many times they happened. Now, this was one of our logs. And you can see in this case, it's pretty clear our main problem here was two-space allocation. And you can see the worst pause there is 41 seconds. So you can also see here that we're failing over into full garbage collections because of allocation failure again. And that's really what helped us diagnose what the pauses were and what was causing them. So as you can see, GC Viewer helps you get a good picture of what's going on in your instance. So I've shown you some healthy logs. I want you to get like a visual idea of what it should look like. And I'm also going to show you some unhealthy ones. So when you go and have a look at your own logs, you'll have kind of a visual cue of whether something's horribly wrong or not. So let's have a look at what it looks like when GC fails. So this is just a garden variety out of memory error. As you can see, there are a lot of full GCs happening here. So those black lines going from top to bottom are full garbage collections, and there's just far too many of them. And at the end of this, they actually just threw an error and stopped. So that error occurs when there's no free space for objects to be created in Eden, and it's almost always just because your heap is too small. On the other hand, this is a large heap with a parallel collector. Now, they're getting really infrequent full garbage collections, but when they do occur, they're taking around 17 seconds. So in this case, I'd probably suggest halving the size of the heap down and monitoring the pauses and seeing if they can go even further. Or alternatively, they can switch to G1GC and see if that works better for them. So this is a similar case where the heap is just far too large, but they've actually restricted young generation to be 1 gig out of their 10 gig heap. And you can tell that, even without looking at the JVM parameters, because that young and old generation are never resizing themselves. You see the yellow and the pink are completely static. So you can see there are really frequent partial GCs on the young generation. That blue sawtooth pattern is really tight together. And then when a full GC occurs, again, it's taking around 17 seconds. So the first step in this case would be to remove that young gen tuning, so you're allowing it to resize for what it needs to, and then probably just reducing the heap down too. So this is another case of the heap just being too large. In this case, we have a 15.5 gig heap, and you can see that the partial GCs are really infrequent. It's almost not even a sawtooth at that point. But each one is taking over half a second, you can see from the times there. And the heap drops down from 4.5 gig. With every collection, it's dropping down to under 500 meg. Is that working? No. Are we stuck? Tech support? Yeah, maybe. Let's do it again. Yeah, okay, thanks. Yeah, that's fine. Yeah, that's where I wanted. Perfect. Okay, so this is what our case looked like. So here you can see our 41-second two-space allocation failure. It's that big grey bar in the middle. And it's grey because it's a young generation collection. So we were failing when we were trying to promote from Eden into Survivor. And then you can see at the bottom it's actually failing over into a full garbage collection, which is another 4 seconds of pause. And this one, obviously it's a pretty catastrophic failure. In this case, we're just seeing full GC after full GC, and the heap just isn't able to reclaim enough space to continue. So the next GC is starting almost as soon as the one before it ends. So in this case, the problem is actually to do with a memory leak in a plugin. So it's not something you'd need to tune GC for at all, which is just something to bear in mind. GC can fail because the heap is tuned poorly, or it can fail because there's something going wrong in the application. And it can be pretty hard to tell the difference between the two, but if you follow best practices and your GC is usually behaving well, but you have occasions where crazy stuff like that happens, then you might be looking at an application problem. So how do you solve these problems? Well, out of memory errors, if it's Java heap space, it's probably just because your heap is too small. So increase that heap, but do it by small increments, and keep an eye on the logs as you do. So your young generation pauses will get longer, and if you're using serial or parallel, so will your full collection pauses. Now, if it's because your heap is just too large and you're getting really infrequent collections, you can just decrease the memory. It's actually much safer than a lot of people think. But again, just keep an eye on those logs and just watch what change is actually happening. So if you're having really long pauses, use that event details tab in GC Viewer to try and diagnose the types of pauses, and from there you can plan and figure out a way to solve them. So we've talked a lot about how garbage collection works and what it looks like when it goes wrong. So how can we avoid it going wrong? So let's have a look at some best practices. So the first step is always to benchmark. From there, you can make a plan, make a small change, measure the impact of that change, and repeat until you get the outcome that you want. So what outcome do you want? Well, there are 3 basic goals that you can aim for. You have latency, which is the max individual pause time for each pause. Throughput, which is the time spent serving requests. So out of a minute, how many seconds are spent serving application requests versus performing garbage collection. And footprint, which is the size of the heap. So you can tune for 2 out of 3 of those goals, and you will have to sacrifice the third. So you can't have short pause times, 99% throughput, and a really small heap unless you're not really using the application. So if you want low pause times and high throughput, you're going to have to sacrifice footprint. And the best way to do this is to use G1GC and a large heap. So you'll have short pause times, lots of time spent serving requests, but you will need a larger heap to do it. So you might have this goal if you're running data center, where you can't afford long pauses that can mess with nodes communicating with each other, or if you want high availability and responsiveness. Now, if you want low pause times and a small footprint, you'll have to sacrifice throughput, which means you'll have a lot of individual pauses that are individually very short, but they will be closer together. So out of a minute, you might find you only have 50 seconds of time spent serving requests, but that's not going to be one big 10-second pause. That 10 seconds will be split up into around 50 pauses of 200 milliseconds each, and they'll be about a second apart. So it's something your users are unlikely to feel. So you might tune for this if you're constrained by memory on a VM, for example, or perhaps you have scripts that will time out if they don't get a response within a certain amount of time. So you'll have short pauses, but they'll be closer together. Now, if you need to have a small footprint, but you want high throughput, you'll have to sacrifice pause times. And the best way to do that is to use a parallel collector and a small heap. So you'll have full garbage collection pauses that will be longer than if you were using G1, but if your heap is small, they still shouldn't be something your users will feel. So you might tune for that if you have an application that normally runs really well, but occasionally performs tasks that use a lot of memory, like a space export in Confluence. So this will allow the application to deal with that influx of objects as quickly as possible, but it will pause while it does. But those longer pauses will be further apart, so you'll still have good throughput, and it will allow you to keep that footprint really low. So this is all pretty complex, but the good news is that the JVM is doing this for you on every single collection. So the first goal that the JVM tries to meet is latency, so low individual pause times, and G1GC aims for no longer than 200 milliseconds. So if it meets that, the next goal it will aim for is throughput, so less frequent collections and more time spent serving requests. And the default for G1 is 99% throughput and 1% garbage collection time. So if that throughput goal is not being met, the JVM will increase the heap up to the maximum size that you've specified, and it will change the size of young generation and tenured generation to try and get the best performance. But if latency and throughput goals are both being met, the JVM will try to resize the footprint back down towards the minimum. So some of the common mistakes I've seen customers make and that we've actually done ourselves are, firstly, just increasing the heap too much. So your young generation pauses will get longer, and if you're using serial or parallel, so will your full collections. So back in my support days, I once helped out a customer who had had some out-of-memory errors, and so they had increased the heap up to 40 gig to deal with it, and they were using a parallel collector. So they would run for days or sometimes weeks without any garbage collection at all, but when they happened, they would take up to 5 minutes. So at that length, it really feels like the application is just frozen, and so then they would reboot at that point, which just means even more downtime on a mission-critical system. So people are often afraid of dropping the heap down. It can seem counterintuitive. I mean, we all come from the world where if you have a problem, you just throw more memory at it and hope it goes away. But in some cases, it really can be the best thing that you can do. So we got this particular customer down to 8 gig, and they still have some pauses, but they were shorter and more frequent and within acceptable limits. So if you are going to increase your heap, use G1GC and increase your CPUs as well. So you get roughly 1 garbage collection thread per core. So up to a point, the more CPUs you have, the better GC performance you'll get. So secondly, there are some parameters which will stop the JVM doing all of that auto-tuning, and that can be really harmful. So once you set hard limits, the JVM can't adapt to what it needs to in that moment, and you'll often add a parameter to get rid of one type of error just to hit a different error further down the track. So the JVM really is much better at this than we are. So if you have to tune, if you're having a problem and you have to, don't increase the heap more than you need to, and rely on soft tuning parameters. So soft tuning parameters are more like suggestions. They still allow the JVM to auto-tune as required. So let's have a look at some of those hard tuning and soft tuning options. So let's say your benchmarking has led you to the conclusion that your young generation size is too small or too large. You have a couple of options. So you could explicitly set the young gen size using max new size, and that means that young gen will never be able to increase over 2 gig, even if it needs to. What you get at that point is either out-of-memory errors or objects being promoted too quickly into tenured, which can cause other problems. And that's what we saw earlier in that GC viewer example. So you see the generations aren't resizing themselves. You see the young generation collections are happening more frequently than they need to. And when full garbage collections happen, they're just too long. So the soft tuning option, on the other hand, would be to set the ratio of young generation to tenured. So in this example, the ratio is 1 to 3. So young generation would be 1/4 of the heap, and tenured would be 3/4. But because it's a soft goal, the JVM won't throw an error if it needs to exceed that at any point. But on subsequent collections, it will just resize back towards that goal. So let's say you've noticed you've got low throughput, and you'd like to try to restrict the time you're spending in garbage collection. So you could set a hard limit of 10. Or you can set a soft ratio of 1 to 9. Now, these will actually achieve the same thing. They're both aiming for 10% of time spent in garbage collection. But if you use GC time limit and you have collections that go over 10%, you will throw a GC overhead error and your app's going to go down. Whereas if you use GC time ratio, on the other hand, it's more of a suggestion. So the JVM will use that goal to tune for throughput as it goes. And if it has to go over that 10% at any point, at least your application won't go down. So another option there would be to increase the pause time goal. So that will allow individual pauses to run a little bit longer so they can process a little bit more each time, and therefore they won't have to be as frequent. Now, in our case, we were having allocation failures trying to promote objects from Eden into Survivor because there wasn't enough space in any Survivor region, and all the regions are already allocated. Now, Survivor is 1/8 of young generation by default, so it's 1/8 of 40% of your heap, so it's actually really small. So you could explicitly increase that ratio of Survivor using this parameter, and it would probably fix that particular problem, but you're likely to run into other allocation problems if you have regions allocated into Survivor, but they're sitting empty and they're required for Eden or tenured. So alternatively, as we did, you can increase the amount of reserved heap to be reallocated to any required region. So those soft parameters allow the JVM to tune automatically as it normally would to try and meet those goals of latency, throughput, and footprint. You're just giving it some suggestions of what you'd like it to prioritize. So the things I want everyone to take away from today really is that tuning is hard, and you should avoid it if you can. If it ain't broke, don't fix it. If you do have to tune, if you do have a problem that leads you to this, tread carefully, keep it as simple as you can, and use soft parameters where possible. So have a plan, know what your goals are, and know how you're trying to achieve them. And for every change you have to make, benchmark, make a small change, measure the impact of that change, and then repeat until you achieve that goal. So what you guys can do when you get home, have a look at the current state. So have a look at your logs, check them out in GC Viewer, get a benchmark of where you're at right now. Think about what your goals are, whether you need latency, or throughput or footprint. You likely won't need to do anything at all, but if you do, set out your goals and plan out how to achieve them. So in either case, be minimal. Remove any unnecessary parameters that might have been added in the past to solve problems that might not be necessary anymore. And if you do need to add any parameters, add one at a time and measure the impact of them. And if they're not helping, just remove them again. So where you can get help with all of this, you guys can either take a photo or you can grab it off of the recording later for those URLs. Atlassian's documentation, we've actually written out that whole tuning guide for latency, throughput, footprint. It's huge, it's complex, but it will help you get to your goal. Oracle's documentation is also fabulous. They have really in-depth descriptions of all the collectors. They have the default for every single parameter and what will change if you change those parameters. And hopefully I've managed to talk you out of tuning for the fun of it. But if you do have a problem and you have to tune and you're stuck, you can contact support. They are an excellent bunch of people. They're here to help you, and support is included in your maintenance. So please get in touch. Thank you.
Thank you. Thank you, Denise. That was awesome. We have a few minutes for questions. So we do have a room monitor who's walking around with the microphone. So if you want to raise your hand, he can answer that question. In the meantime, I do have a question from the app here. Tell me if this sounds right. Do you recommend setting XMS and XMX to the same value to ensure efficient garbage collection?
We do. That is our official recommendation, yes. And the reason behind it is because, as you can see with that resizing of young generation and old generation, you're actually resizing the whole heap at the same time. So with every collection, it will try and pull it down towards XMS, which is the minimum. And then as you're using it, it will increase up towards XMX. So there is just a little bit more overhead in every collection if you're trying to do that resizing of memory as you go. So if you're having problems, if collection's taking a little bit too long, resizing them to be the same at least takes out that little bit of extra overhead of sort of growth and shrinking.
Gotcha, cool. And looks like there's a hand in the back here. If you, or oh yeah, do you want to go ahead and ask your answer?
Yeah, I was wondering what was the problem that led to the database connections all being used up?
What was that?
Are you fiddling with your microphone?
I did, I fiddled, I'm sorry. Do you know what? I actually can't recall what it was. I think it might have just been a lack of caching and a whole bunch of use at one point, and that just led to all of the connections being exhausted. I think we also, because it's data center, we've got 3 nodes coming into one database, and I think we potentially had, Postgres has 200 connections by default, but 3 of those are reserved. So if you split out those connections into sort of 3 lots and you're expecting to be able to allocate 200 connections, you can't. So I think it was that happened. We just kind of hit the absolute maximum and then tried to use reserved connections and failed.
Looks like there's another question in the back. While we're moving over there, there was a question about where you enable more verbose garbage collection logs in JIRA and Confluence.
Where?
Yeah.
You do? It's just a JVM parameter, so I think it's just like plus GC verbose logging. But you can just Google for verbose logging and you'll find that parameter really easily.
Great. Back here?
Yeah, something that's been, I guess, a little bit of a point of frustration, but also curiosity is, I've noticed over the years that the different applications on default install have different JVM tuning parameter set. So some of them will have XMS and XMX equal, some won't. Some have garbage collection enabled by default, some don't. Yeah. Is there a reason for that? Is there, based on the application's own performance, or?
I mean, every application is different, and the types of objects that are created are going to be different. So the usage pattern for between Confluence and JIRA is different for one. The usage between my Confluence and your Confluence is going to be different again. So there's sort of no one-size-fits-all approach. So what a lot of different apps have tried to do is to sort of set a default that they think makes sense as a good starting point, and then people can kind of tweak and tune that from there based on what they need. Yeah.
So then I guess to follow up on the other question that you got, so when would be a time where you wouldn't want XMS and XMX to be equal? Because I've noticed that it's not in some of the applications and it is in others.
When you wouldn't want them to be equal, I suppose.
But on not on an environment by environment basis, but an application by application basis. Like when would that not be a safe starting point?
I don't think it's ever going to be an unsafe starting point. I think it's it just adds that tiny bit of overhead which you may not want. We do that on cloud, actually. So XMS and XMX are not set to the same, and it's because we want to be able to release that memory to be used by other applications that are running on the same VM.
Okay. It can be confusing at times when you see different defaults in each one and you kind of don't know what you should be going with to try to standardize
it's because there really just is no one-size-fits-all approach. Yeah.
Great question. Another one, again, raise your hand if you have another question, and our room monitor will move over. There was a question about coming from Microsoft hypervisor cluster environment. How does one decide on resources when faced with another company's quote-unquote best practices?
Good question. I think, everyone sort of has different experience that will give them a best practice approach. My best practices come from 5 years of supporting and developing Confluence, so they may not be best practices for another application. They may not even be, like the defaults may not even make sense for your application and your usage. So I think it's one of those things where it's just really hard to say, this is the right way. There is no right way. It's just the right way for your application in that moment.
Great. And question over here.
Yeah, the visual tools are very helpful, but you have to have enough experience to see the patterns, I think. Do you have any tools that can be a little bit more concrete in giving recommendations? They can look at the logs and say, well, this is below the standard we expect. this is the steps you take?
Yeah, there is one, and I, of course, can't think of the name of it right now, so you might have to come and ask me later, and I can find it for you. There are a lot of paid tools as well that will give you some kind of recommendation on what to change based on what's actually coming through in your logs. But yeah, that's an excellent question.
Great. Again, if there are any other questions, raise your hand. I think we have maybe time for one more. Okay, then we'll get one from here. There's a question here about how to know which plugin is causing the issue. Is that related to garbage collection?
Not necessarily, but I can give you a tip. If you think it's a plugin, you've got safe mode in all of our applications in the UPM. So the best thing to do is just go into safe mode, enable safe mode, and then if the problem goes away, it's a plugin. You can enable each plugin individually after that, one by one, and then you can figure out when the problem starts happening again. You can really isolate which plugin it was. And that's kind of the easiest way to do it without having to uninstall and reinstall plugins.
Awesome. Well, let's give Denise a round of applause. Thank you, Denise. That was awesome.
Thanks. Awesome.